Okay, so this is the I direction and this is the J direction. X and Y axes, if you like, but they're unit vectors in those directions. And let's draw a unit vector up here, call it A. It's a unit vector in the A direction though. And let's have it have an angle of alpha from the I direction there. That's no big deal. Let's also have a vector B, which is also a unit vector, but let's pop B out there somewhere, and its angle is beta. And let's have a vector C, which is the same angle as beta, vector C, but you've got to go down that way to get there. So I've set it up so that my three vectors, A, the size of that is 1. And vector B, the size of that is also 1. So vector A size equals vector B size. And vector C, the size of that is also equal to 1. They're unit vectors. I did that just to keep things simple. I could have done them at other sizes, but I'm wanting to show you something pretty cool. I'm wanting to develop the compound angle formulas for cos using vectors. So the first thing is to write A, B and C in component form. So vector A is equal to. Now, we want to know how much of A is in this direction across here, and that'll be cos alpha times I, and how much of vector A is in this direction up here, and that'll be sine alpha times J. So that's pretty straightforward. Now, I could flesh that one out for you if you wanted me to, but I think that's fairly obvious. But just to show you how you might find the amount of A that goes in the I direction, so the projection of A in the I direction, that would be A dot I in the I direction. Now, that'd be the size of A times the size of I cos the angle between A and I, which is alpha, in the I direction. Now, size of A is 1, and we know the size of I is 1. That's what I is, a unit vector in the X direction. So that's 1 times cos alpha times I. So that's where we get cos alpha times I. I could do a similar process and work out the projection of A onto J, and it would turn out that it's sine alpha times J. So let's just accept that. And under those circumstances, it's quite straightforward to see that vector B can be written in component form as cos beta times I plus sine beta times J. Now, what about vector C? Vector C is a little bit more confusing, I guess. The projection of vector C in the I direction, that's no big deal. You can see that vector C is out there in a positive way in that direction. But vector C goes downwards, not upwards. So it's actually going to be a negative in terms of the J direction. Anyway, it's straightforward to see that it would be cos beta times I. And I could go through a process like that to show that. But I'm saying it's going to be minus of sine beta times j to write this purple vector, vector c, in component form. Now, if you were to work that through in terms of the projection of c onto j, then it would be c dot j times j. That would be the projection of this vector c in the j direction. That's the actual vector way of working it out. Now, c dot j is the size of c times the size of j times the angle between c and j, and the angle between c and j is all of that, which is actually 90 plus beta. And cos of 90 plus beta, well, that's 1. And cos of 90 plus beta is the same as sine of minus beta. From your trigonometry, we know that. So this, in the end, this will be minus sine of beta j, which is what we've got here. So I've written my three vectors, A, B and C, in component form. Once I've got that set up, I'm able to do some dot products in two different ways, in terms of components and in terms of the size of the vectors and the angles between them. Equate those two different ways and see if I can develop those compound angle formulas. So, let's have a look what we can do in terms of dot products. So the first dot product I want to do is A dot B. A dot B. So, in terms of the components, it'll be cos alpha, cos beta, plus sine alpha, sine beta. That's one way of looking at A dot B. Another way of looking at A dot B love the colour, is the size of A times the size of B times the angle, cos of the angle between A and B. Now between A and B, let's just have a look back on our diagram. What's the angle here between A and B? I'll put a red dot there on the angle I'm talking about. That's the angle between A and B. Well, if you think that it would be alpha but take off beta, you'd be right. That in there is the angle alpha minus beta. So let's go back here. Cos of angle alpha minus beta. So these two are both equal to A dot B, so they're equal to each other. But let's simplify this even more. Remember, these were unit vectors, so the size of A and the size of B is just 1. So that's equal to A dot B, that's equal to A dot B. So cos of alpha minus beta equals cos alpha cos beta plus sine alpha sine beta, which is a formula that we encountered earlier in this course, but we developed it using the unit circle, using cosine rule, and using the distance formula. And now we're looking at it from a vector's point of view. So, okay, that's A dot B. We could also work out what A dot C is from this. So let's try that. Here's our vectors up the top of the page. And let's work out what A dot C is. Vector A dot with vector C. All right. Component-wise, it's cos alpha cos beta plus sine alpha times minus sine beta. So you just times the I components and times the j components together and add those. So we get cos alpha cos beta minus sine alpha sine beta. We know that because we know that sine alpha times minus sine beta equals minus of sine alpha sine beta. All right, there is another way of looking at A dot C, and that's in terms of the magnitudes and the angles between them rather than in terms of the components. So if I look at the product of the magnitudes times cos of the angle between them, the angle between A and C. Well, let's just look at our diagram again. What's the angle between vector A and vector C? The angle between vector A and vector C is, if I can just, with purple, highlight that for you, I want to find that. Well, that's alpha there plus beta. To get all the way down, you go alpha plus beta. And add those two together. So alpha plus beta. So that'll be cos of alpha plus beta. These were unit vectors, so 1 times cos of alpha plus beta. So we get cos of alpha plus beta. A dot C equals this, A dot C equals that. So these two things are equal because they're both equal to A dot C. So there we have compound angle formula for cos of A plus B, or alpha plus beta, and cos of alpha minus beta, developed from using vectors.